Welcome to Lecture 17 of Electrical Engineering 525. In this lecture, we will continue to talk about linear arrays, and in particular, we're looking at equally spaced linear arrays with linear phasing, and also with the excitations for all elements the same in terms of magnitude. Today, we will look at problem 8.2-2 to help illustrate some of these ideas. So that problem is as follows. 8.2-2 says, use the techniques of figure 8-6 to obtain a polar plot of the array factor for an array of two elements spaced one wavelength apart with currents that are equal in amplitude and 180 degrees out of phase. So if we look at equation 8-4, which is relevant to this problem, we have a situation, we have an equation that applies to this situation, namely In is equal to An e to the Jn alpha. Now this is the condition that was mentioned just a moment ago. This is called linear phasing of the currents. And now notice that at the present time there is no requirement that all the currents have the same magnitude. We will impose that restriction will actually apply to this problem and to the test problem as well, but it's not really a requirement at this stage. In some of the later work that we will do to develop subsequent formulas, it will be a requirement, but for right now, for the work we're doing at this moment, it's not a requirement. However, the linear phasing is a requirement, and it's expressed here by this e to the Jn alpha term. Now recall that in this case it says here at the end of the problem that the currents are equal in amplitude and 180 degrees out of phase. I've decided to express this in this way as say I0 is equal to 1 and I1 is negative 1. Now of course it doesn't have to be 1 and negative 1, it could be 2 and negative 2 or 1.37 and negative 1.37. That doesn't really matter. The point though is that these two currents have been chosen to have equal amplitudes and to be 180 degrees out of phase. Now if we try to fit these two currents, try to choose alpha and the a sub n's so that this equation here will describe these two currents, then obviously one way to do that would be to choose A0 is equal to A1 and both of those are equal to 1, and that will of course agree with the right hand side of this equation having a magnitude of 1, just as the left hand side does, as we can see from these two equations. And then to satisfy that I0 is positive 1 and I1 is negative 1, we could choose alpha to be either plus or minus pi. And in this problem we will investigate both of those possibilities to see if ultimately that makes any difference or not. Okay? Now furthermore, in this problem they are telling us that the elements are spaced one wavelength apart, so that means that d is equal to lambda, and therefore beta d, which is beta is 2 pi over lambda, so beta d is equal to 2 pi over lambda times lambda, or 2 pi, and that's in this case now beta d is equal to 2 pi. Now as we recall from our problem in section 16, the left edge of the polar plot is at alpha minus beta d, and the right edge is at alpha plus beta d. The center of the polar plot is at alpha, alpha, and then the diameter of the polar plot is 2 beta d. So the right hand edge is at alpha plus beta d, the left hand edge is at alpha minus beta d. Now in this case, as we have just observed, beta d is equal to 2 pi, And so that means that the polar plot is going from alpha minus 2 pi to alpha plus 2 pi. Now recall, we've already said that alpha, we're going to investigate two different possibilities. One is alpha equals negative pi, and the other one is alpha equals positive pi. So if alpha is equal to negative pi, then alpha minus beta d would be minus 3 pi, and alpha plus beta d would be positive pi. On the other hand, if alpha is positive pi, then alpha minus beta d would be negative pi, and alpha plus beta d would be 3 pi. So in one case, we have the polar plot going from minus 3 pi to pi, and in the other case, we have the polar plot going from minus pi to 3 pi. And we're going to go ahead and plot both of these cases. The one that we will do first is alpha equals negative pi. So we're going to do the alpha equals negative pi case first. Now recall again from lecture 16 that f, which is the normalized pattern factor, and we're considering f here to be a function of psi, is equal to sine of n psi over 2 divided by n sine psi over 2, where n is the number of elements. And in this case, as we saw above, we have here, you see right here, this is a 2-element array. So n is equal to 2. If we substitute n equals 2 into this equation, we get f of psi is equal to, 2 times psi over 2 will give us psi, and here this n becomes a 2, so 2 sine of psi over 2. So f of psi is equal to sine of psi divided by 2 sine of psi over 2. Now this can be simplified by remembering that the sine of 2 theta, if we think of psi as being 2 theta for a moment, well, that's 2 sine theta cosine theta. So sine of c is 2 sine of psi over 2 cosine of psi over 2. And obviously that is a good expansion to use in this case, because it allows us to entirely cancel out the denominator. The 2 sine psi over 2, that is the first part of that expansion, is canceled out by the 2 sine of psi over 2 in the bottom, and so we're just left with the very simple expression f of psi is equal to cosine of psi over 2. And so that makes this, it makes it very easy to plot f of psi. And once again now, and by the way, this work that we've done right here in simplifying f of psi, this is all completely independent of alpha. So f of psi will also have exactly this same expression in the case alpha equals positive pi. But do recall that at the moment we're looking at the case alpha equals negative pi. And recall also that we said in that case that we're interested in the polar plot going from minus 3 pi to positive pi. So since we're interested in the polar plot over that range, we will plot f of psi in that range. So here we have f of psi as a function of psi. And when we plug in just a few values in this range from minus 3 pi to pi, we can quickly get an idea of what this function looks like. Notice obviously at psi equals 0, we get cosine of 0, which is 1. At pi, we would have cosine of pi over 2, which is 0. At minus pi, we'd have cosine of minus pi over 2, which is 0. At minus 2 pi, we would have cosine of minus pi, which is negative 1, but then we're taking the absolute value of that. See, I need to put one more bar in here to the right. Here, that's the absolute value of that. Didn't do that too well either. Now, so, well, I'll get this right eventually. Now, since we're plotting the absolute value of this function f, then at negative 2 pi we get 1. And then finally at negative 3 pi, we would get cosine of negative 3 pi over 2, which is 0. So after plugging in those values, you can, and of course it varies smoothly between those like a cosine function. And so this is a good approximation to what the absolute value of f of c looks like between negative 3 pi and pi. Now remember our rule: when we want to then form the polar plot from the plot for f of c, what we do is we go straight down, and we've already identified that the polar plot will go from minus 3 pi to pi. So if you wish, you can go ahead and draw the circle for that. And we have extended this line through the origin of the f of c plot. We've extended that down, and that's useful to do because remember that the center of the polar plot will be at alpha, and indeed you can see that is the case here. Alpha, the center in this case is at minus pi, and of course that's the case we're investigating right now, is alpha is equal to minus pi. So we have the center, the circle is located here between negative 3 pi and pi. We have located the center at minus pi. And then the two peaks in this graph are at 0 and 2 pi. And if we extend vertical lines to both of those, we can see where those hit this polar plot. And furthermore, if we extend vertical lines from the zeros, now we didn't actually draw it in here, but you can see that the vertical line through pi, of course, would hit the circle right here at this tip, and the vertical line through negative pi would hit the circle here at this tip. And then we have minus pi is another 0, and that vertical line goes right through here. So the polar plot needs to go, since those are zeros above, the polar plot needs to go to 0 at those locations, and in fact obviously it does there, and at theta equals 0 degrees, and here at theta equals 180 degrees. And here at these locations, denoted by this radial line and also by this radial line, the polar plot must have a magnitude of 1. And so that's how we get these two lobes. And these two angles, you can see from the picture really that these two angles correspond to, again, remember we're measuring theta from the positive z-axis, which is here to the right. So we have, for this main beam, we have 60 degrees, and for this grating lobe to the left of the main beam, we have 60 degrees measured from the negative z-axis, or in other words 120 degrees. And of course the grating lobe has the same, in this case, same magnitude as the main beam. So really it's indistinguishable from it, except it's going off at this angle 120 degrees from the positive z direction. This one is, the main beam is going off 60 degrees from the positive z direction. But and of course, if we wanted the full pattern, as we mentioned previously, we would reflect this about the z-axis, and the pattern here would look like just would be exactly the reflection of these two lobes, and that would give us the pattern for this two-element array. Now again, that is the result that we get if we regard alpha as being minus pi. What if we regard alpha as being positive pi? Now, physically speaking, let me just remind you that physically speaking, alpha is coming in here in this linear phasing requirement, And we can see here that whether we chose alpha to be equal to pi or alpha to be equal to negative pi, that would make no difference in these currents. And so if it makes no difference in the currents, then ultimately it cannot make any difference in the pattern. But let's make sure that that is the case. So let's go ahead now and investigate the other alternative, alpha equals positive pi, and see that we do indeed get the same result. So here we're finished now with alpha equals negative pi. Let's now look at the case alpha equals positive pi. Okay, as we've already noted, for alpha equals positive pi, the pattern looks the same. Oh, excuse me. Yeah, sorry, I got a little ahead. Here's where we should begin. So here, now consider alpha equals pi. Now, as we've already said, the pattern, the normalized array factor, it has the same expression as before, cosine of c over 2. But now this plot, since the current is now at positive pi, we are going to plot from negative pi to 3 pi. And so when we plot this, again, we're going to plot the magnitude of f of c. So I need to put the vertical lines here and here. When we plot the magnitude of f of c down here as a function of c between negative pi and 3 pi, well, again, at negative pi, this would be cosine of minus pi over 2, which is 0. At 0, we'd have cosine of 0, which is 1. At pi, we have cosine pi over 2, which is 0. At 2 pi, we would have cosine of pi, which is negative 1. But then when we take the magnitude, we get positive 1. And finally, at 3 pi, we'd have cosine 3 pi over 2, which is indeed 0. So this is what the graph looks like in this case when alpha is equal to pi. And just as we did before, we then draw our polar plot below. Now the polar plot is going from minus pi to 3 pi. And we can drop down a vertical line from 0. And then when we go to alpha to find the center of the circle, it is indeed at pi, which is what we expect. And then we drop down vertical lines from the two peaks at 0 and 2 pi. And so we get these two lobes, and if you wish, you could drop down the lines for the 0 points as well, but it's not really necessary in this case. I think we have a very good idea already of what the pattern looks like. And notice that here, if we consider the main beam here to be the one under c equals 0, then in this case, the main beam is at 120 degrees, and the grading lobe is at 60 degrees. But the plot, of course, looks exactly as it did before, which, of course, is what we expect since the currents are exactly as they were before. And one last observation here is to say, okay, so for alpha equals pi, the pattern looks the same. But the main beam is at 120 degrees, and there's a grading lobe of the same size at 60 degrees. Whereas before, we said, so for alpha equals negative pi, the main beam is at 60 degrees, and there's a grading lobe of the same size and shape at 120 degrees. So the graphs look the same, but if you adopt the convention of always considering the main beam to be the one where c is equal to 0, then in this case, we would call this the main beam at 60 degrees, and then in this case, we would consider this one to be the main beam. And notice that that is consistent with what we have learned our equation. Okay, so, well, here's our summary. Alpha equals negative pi, then theta naught is equal to 60 degrees. Alpha equals positive pi, theta naught is equal to 120 degrees. And notice that that's consistent with the equation that we've learned. Alpha is equal to minus beta d cosine theta naught. Remember, beta d is 2 pi, so this becomes alpha is equal to minus 2 pi cosine of theta naught. And so, in fact, we'll go ahead and plug that in, minus 2 pi of cosine theta naught. And so when we check theta naught equals 60 degrees, we would get minus pi, as we are noting right here. Theta naught equals 60 degrees corresponds to alpha equals minus pi, and theta naught equals 120 degrees would correspond to alpha equals positive pi. So this equation, this equation alpha is equal to minus beta d cosine theta naught is indeed consistent with our results from the polar plots. And so now let's look at test 17. That concludes what we want to discuss here in lecture 17. And now test 17 is to give you a little more practice with some of these ideas. Okay, in test 17 we have again a two-element array, but in this case the currents on the two elements are equal in magnitude and phase. Remember, in the problem we just did, the currents, it was also a two-element array, but in that case the currents were equal in magnitude but opposite in phase. Now they are equal in magnitude and equal in phase. And so you are given now 4 polar plots. Here's A. All 4 of those lobes have a magnitude of 1, but the 2 that are vertical are rather thin. The 2 that are horizontal are rather thick. And again, remember now, this is the z direction. Okay, for plot B we have this, and notice it also has 4 lobes, but only the 2 vertical lobes have a magnitude of 1. The other 2 lobes do not have a magnitude of 1, it's smaller. And then for plot C, we have just 2 lobes, both have a magnitude of 1. And then finally for plot D, we have many more lobes in this case. Sorry about that. I guess I shouldn't be recording near an open window. But anyway, in plot D, we have many more lobes, as you can see. And so the questions for test 17, very simple. Which of those plots is for the case D? Now remember, D is the separation between the 2 elements. Which of those plots is for D equals lambda over 2? Which of those plots is for D equals 3 lambda over 4? Which of those plots is for D equals lambda? And finally, which of those plots is for D equals 2 lambda? So basically what we're trying to do in this test is to get an idea of what happens to the polar plot as you increase the distance between the elements. And this test should help you to begin to develop some intuition for that question. And so that concludes lecture 17, and good luck.